I am about to call for the bell word. So I'm looking for 4 out of 6 marks here for a point. 4 out of 6. Let's see. Who was called this week already?
What are the odds? They can't call me right.
Who got called this week?
Hmm?
Who got called this week already? Kaylee? And Caesar? Okay.
Can't call me?
If it's me, I'm gonna anybody.
So what's the last week?
Last class.
Last week, I'm gonna call me.
All right.
It's gonna be me.
It is for Daniela Gutierrez.
You were struggling too.
Wait. Oh no. 2. All right. So we're gonna go ahead and go to answer these questions. Let me get my handy dandy calculator. So the key in this first question, just to explain it, is to recognize that if the time is the same and the current is the same, they both have the same amount of coulombs. So they have the same amount of coulombs. So that's the key to solving this question correctly. So the first thing is to start with your mass of tin metal and to get to coulombs from there, which you totally can do. Because at the cathode, 10 to plus 2e minus goes to 6.
It's just half
Right.
of that.
That's the tin metal that's being made. So what do? Remember, at this time, we go 2.95 grams of tin, and then what do we divide by? The molar mass, which is 118.7, I believe, grams in 1 mole of tin. And then we say 1 mole of tin is 2 moles of electrons. And then you can take it one step further and say that 1 mole of electrons is how many coulombs?
9.65
or 96,500. And so this gives us 4,805.7 coulombs. That's the amount of coulombs transferred for tin. The clue is that's the same amount of coulombs transferred for aluminium, right? So what's the information for aluminium? Al plus 3 electrons goes to Al. So what you would need to do is go with your same amount of coulombs, 45.7 over 1 times 96,500 is 1 mole. 3 moles of electrons for 1 mole of aluminum. And then we need to be grams, right? Grams would be 1 mole, 27 grams. Which gives us our answer is 0.447 or 0.45 grams. You could have done this in less steps. You could have actually, once you got to the moles of electrons, went from moles of electrons transferred in tin directly to moles of electrons transferred in aluminum, if you understood that connection. And then you would have had the 2 over 3, and the math would be the same. But that is the idea of what you would need to do. So if you got this answer, you had to show your work, like what you multiplied and divided to get there, and this would be worth 2 marks. All right, I'll pause for anybody who is finishing writing this down or needs to take a picture. And then we're going to go to the bell word 2, which is a redox titration, which we did a redox titration last class. And based on this bell work, we need to continue doing more titrations. So we're going to do another titration in unit 4 to keep practicing titrations. Anytime there's an opportunity. All right, so bell word 2, they tell you that potassium sulfite is used as a food additive. Yum. You could look up on your own what do they add potassium sulfite to, but it's probably not a very high concentration at all. So the concentration of sulfite, and these are usually used as preservatives. Typically, you add these ions to preserve your food.
They eat it?
I don't know. It's probably, I have to guess that it's kind of It doesn't taste exactly like salt, but it's in that category. So the concentration of sulfite ions can be determined by titration using aqueous acidified permanganate. And they give you a method. They take impure, which means it's not just potassium sulfite, it's got other stuff in it. And they make a 250 centimeter cube solution of that. Then they take out 25 centimeters cubes and use that for the titration. And they titrate it against a known amount of acidified MnO4 minus to reach the endpoint. So a very standard titration question. All the sulfite ions are oxidized. None of the other species in K2SO3 are oxidized, so you can assume that that's the only thing that's reacting, is what they're trying to tell you here. And then they give you the two half equations. How nice, you don't have to make them yourself. They give you the half equations, and all you've got to do is balance them against each other. So that means you're going to be doing what for the first equation and what for the second equation. Times 5 here, and times 2 here. Because you have to make sure that the electrons transferred are the same. So now I have, for my first one, I'm going to rewrite it over here. That's why I gave you space. 5 waters plus 5 SO3 2 minus goes to 5 SO4 2 minus plus 10H plus 10 electrons. And the second one would be 2 MnO4 minus plus 16H plus 10 electrons goes to 2 Mn2 plus 8 H2O. Then we cancel out anything that's the same, right? So the electron's gone. There's H pluses on both sides. So what I would do is take 10 away from here and leave how many on this side? 6. And then on the waters, I've got 5 over here and 8 over here. So 5 and 8, this would become 3. And then we just write everything that's left, right? So our final answer here would be 5 SO3 minus 2 plus 2 MnO4 minus plus 6H plus. And on the other side, we get 5 SO4 2 minus plus 2 Mn2 plus plus 3 H2O. And that is worth how many marks?
Wow.
1 mark. But you need that mark for the next part because you need it for the titration. The balanced reaction must be used for the titration. So it says calculate the percent purity of the sample of K2SO3. What this means is how much of that impure sample is actually K2SO3. So we know that the impure sample is 3.40 grams. We don't know how much is K2SO3. That's what we're trying to figure out, right? And that's going to give us the percent purity. So how can we find out how many grams of K2SO3 we actually have? That's where your titration math comes into play, right? You have, to read through here, you have the concentration of permanganate and you have the volume. What can that give you? The moles of permanganate, right? So we're going to start with concentration equal mole over dm cubed, right? Concentration is 0.0250 and dm cubed is 0.02240. And so if you multiply by 0.0250 and 0.02240, that's the first step here. You would have got that 1 mark. So that was the 4th mark that you needed, was to recognize the start there. So then when I did that, I got 5.6 times 10 to the negative 4 moles of MnO4 minus. But what am I looking for? I'm not looking for that. I'm looking for sulfite, right? So what's the relationship between permanganate and sulfite? Whenever I go from one substance to another substance, we do a process called stoichiometry. So we need the number in front of MnO4 minus in the balanced equation and the number in front of sulfite. So we know it's a 2 to 5 ratio. And so that's what we put in here. 2 moles MnO4 minus is for 5 moles sulfite. And that gets us to sulfite. But we want to get from moles to grams. So what would we do after that? So we got 0.0014 moles of sulfite here, but we need grams. The first thing to recognize is that K2SO3 has one SO3 in it. So the molar ratio is 1:1. So you can literally just take this amount of moles and multiply by the molar mass of K2SO3. So you would need to multiply by the molar mass of K2SO3, which is 153, which is 158.3, right? And so that gives us, I believe it's 0.2222 grams. But there's one thing that I've left out, and I realized it when I was solving it the other day. This is the amount of grams, not in 250 centimeters cubed. This is the amount of grams in how much centimeters cubed of the solution? In 25, right? So how could I figure out the amount of grams in 250 centimeters cubed of the solution? Go ahead, Issa.
You have to find the concentration of the
No. Close.
Yeah.
By 10. Multiply by 10. Because if I've got the grams in 25 centimeters cubed, I have to recognize that 250 is 10 times that amount. So I should have 10 times the amount of grams. So how Cambridge always writes it in their mark schemes is they write 25 on the bottom and 250 on the top, basically saying that this is how much we have and we need to go back to how much was in 250. So it's 10 times the amount. So we should have 10 times the amount of grams. So we actually have 2.22 grams. And then we're still not done. This would have been us 2 out of 3 marks. If you got to 2.22 grams in your work, you got 2 out of 3 marks. So where's the third mark? This ain't a percentage. You have to go back into the formula, which is 2. So you end it by saying, okay, 2.22 grams over 3.4 grams, which was the impure, right? Multiplied by 100, and your correct answer was 65%. 65.3 or something like that percent, if you had done the process correctly. So, a lot of work. But it's a common type of titration question. You need to keep practicing titrations. That's why you notice me giving you titrations and titration questions commonly, because it can and will show up at the end of the year. All right, so we're going to go ahead and get on to today's lesson. In my opinion, I think electrolysis is a little bit more difficult, and I think what we're going to learn in these next 2 lessons is actually a little bit easier, the voltaic/electrochemical cells. So this is actually a 2-part lesson, so you won't have any homework assigned to you today. However, whatever parts of the homework that you can do, you should attempt while it's fresh, but the homework is going to be due after next class's lesson, which is on Wednesday when we do the math part of it. So today, what we're going to learn is voltaic/electrochemical cells. And so these cells is where we convert chemical energy into electrical energy. Harnessing the actual energy within the chemicals themselves. And so this is the type of cells we use for spontaneous reactions. So these are used in spontaneous reactions. That means this reaction happens on its own. We don't need to add a battery to make it happen. Bless you. And so we're going to be taking a look at the key differences between voltaic cells and the electrolytic cells, which we had been looking at before. And today our goal is a lot of definitions. We're going to get through a lot of definitions again. We're going to learn how to build a cell. And like I said, in a couple of weeks, you'll be building your own cell. So you'll be doing a lab where you actually build your own of one of these types of cells. It's because I'm recording. I have my mic on. All right, so ready? So main idea, we are looking at the second type of cell. There are 2 types of cells we have to study. We learned the first one. I think that one's a little bit more difficult, actually, especially with the aqueous solutions, figuring out what comes out at the anode and the cathode. And this is the second type, which is the reactions that happen on there. So with that being said, let's go ahead and get started. Here's our learning objectives. This is actually not a scary amount of learning objectives. That's kind of like a sweet spot. It's got 4. So whenever you see like 1 objective. It's like, oh, this could be heavy math day. But this does not have heavy math in this lesson. So here we go. Definitions though. Define the term standard electric potential and standard cell potential. That means they will ask you for word definitions for these. And then the next thing is deduce from E values. So these are going to be voltage values, pretty much. The relative reactivity of elements, compounds, and ions as oxidizing agents and reducing agents. So you're going to be given numbers. So you're going to be given these. You will not have to memorize the electric potential values. You will be given them. There's only one potential value I would assume you need to memorize, and I'll tell you why later. The one for the standard hydrogen electrode. You will need to be able to describe the standard hydrogen electrode. Including in this, you will need to be able to draw a diagram of a standard hydrogen electrode. In terms of description, they usually ask you to draw a diagram of it. And then finally, we're going to look at how we measure standard electric potential, like what is the actual setup, the experimental setup, when we have metals or nonmetals in contact with their ions in aqueous solution, or ions of the same element in different oxidation states. So we'll be looking at building all types of cells today. So decent amount. We're going to start with a lot of vocabulary just to make sure that we understand what's being talked about. And then we're going to learn how to build the cells today. And then we're going to do the math next class on Wednesday. Ready? All right. So I had already mentioned the difference between the two types of cells we're learning, electrolytic cells versus voltaic cells. One of the confusing things about this unit is voltaic cells go by 3 different names. I'll go ahead and write them out for you. Some people call them voltaic cells. Some people call them electrochemical cells, which we saw already is shown up as an electrochemical cell. And some people call them, and I don't know, you can look up the etymology on this. I'm not the etymologist. Goodness. But you can look up the etymology. The third one is called a galvanic cell. Like, where does that come from? That wording. And they're all the same thing. So that means whoever's published the question, whether it's a source from an AP Chem class, an ACE class, they might call it slightly differently, but it's actually describing the same process that's happening. And so the electrolytic cell was the first one we learned, which was for non-spontaneous reactions, right? So in an electrolytic cell, we make a reaction happen that's not supposed to. We make sodium, for example, we force its electrons back on it that it wanted to lose. So we supply energy to make that reaction happen. That's what we've been discussing up until this point. Now we're going to be looking at a voltaic cell. So the voltaic cell, the second type of cell type number 2, this facilitates a transfer of electrons that already would be happening in a chemical reaction. So it facilitates the redox process between what's being oxidized and what's being reduced. It basically harnesses the energy out of it. And so this facilitates the transfer of electrons. And the key difference here is you don't have a power source. There is no battery. The actual electricity and the voltage that's created will be from the reaction that's happening on its own. So this will be the chemical energy that's transferring into electrical energy. And that's how batteries work. Like standard batteries are voltaic cells. And so electric potential is your first thing you need to be aware of. We call this E, capital E. So whenever you see a number and it says capital E, this is called electric potential. And this is an amount of voltage measured for a half cell compared to another half cell. And the values that you're going to be given are always going to be compared to something called the sheet, the standard hydrogen electrode. And the reason why all the values you're going to be given are compared to hydrogen is because hydrogen is going to be our baseline of 0. So everything's going to be either above 0 or below 0. And so, yes.
What is this hydrogen?
It's coming. That's why I said there's a lot of definitions at the beginning. I think I have it. I tried to put it really early but I can even tell you on the next slide to show you what a half cell is. So this is the look of an electrolytic cell versus a voltaic cell. So this is for the spontaneous reactions. And this is for the non-spontaneous reactions. So I want you to see what's going on here in the voltaic cell. The first thing you asked is, what's a half cell? This, for example, is a half cell. It's where either the oxidation is taking place or the reduction is taking place. So in a voltaic cell, you have this setup where you've got one area where electrons are being taken from and one area where electrons are being supplied. Notice this is staying the direction of electron flow. It's going this way. That actually tells us some very important information. Electron flow is always from the anode to the cathode. So electrons will always flow from the anode to the cathode. You're going to want to write that down. Why? This is where reduction is taking place. So this is where reduction is taking place. And this is where what's taking place? Oxidation is taking place. So if I have the direction of electron flow, I know what's being oxidized and what's being reduced. Typically, what's going to happen is they're going to give you E values, and from the values, you're going to have to figure out what's being oxidized and what's being reduced, but we haven't gotten that far yet. So this is a half cell, and this is actually the cathode, and this is another half cell. This is the anode. And so what happens here is the following. If this is oxidation, what process is taking place here? Zinc is turning to zinc plus 2. And if this is the reduction, what's taking place here? Copper plus 2 goes to copper. So if this is where zinc is being turned into zinc 2 plus, where are the electrons going? But there's no copper here. The zinc, notice, is in a different beaker from the copper. So where are the electrons going? As zinc's oxidized, remember this, there's 2 electrons. Where do they go? They actually are going here, right? And they're, as this is taking the electrons are flowing to the cathode. And they're flowing through this wire. Does that make sense? So through the wire that's up here, this is a wire, it's made of a metal. There's electrons that are going to flow through that wire that are taken from the anode and going to the cathode. And so then there's electrons here, right? And the electrons that gather here supply electrons to the copper 2 plus to make it to become copper. Does that kind of make sense?
Why don't we need sodium?
So that's coming. In order to keep a charge balance and also to complete a circuit, you actually have to close a circuit. I don't know that more than just a few of you have taken physics, but even when we did previous chemistry, we did a little lab where we did circuits and we tested solutions. If you don't close the circuit, like if you have a part that's not connected, no electricity can flow. You need a closed circuit for electricity to flow. So this right here is called a salt bridge. And in the salt bridge, you have any ionic compound really that's not reacting in the mixture that's acting as charge carriers to maintain the flow of electrons so that electrons can continue to flow through the cell. So without the salt bridge, you won't have any electricity being conducted because it has to be able to flow the whole way through the circuit. So it basically works kind of like this. You see that? This completes the circuit. The salt bridge completes the circuit because it's where the charge carriers are. And so, like I said, we'll actually be building this and you can test this. You can test if there's going to be electricity with the salt bridge, without the salt bridge. And you're going to see you need the salt bridge there for it to actually conduct electricity. So interesting stuff. For Cambridge, you're gonna have to be able to draw this. There are usually 3-mark questions where you have to draw this whole entire setup. And we'll be discussing that in this lesson. How do you earn those marks? More definitions. So key components of a voltaic cell. The electrode, where's that? The electrode is placed in each half cell. And notice for these metals, zinc, copper, you're using the electrode of the same type of metal. So if I have a solution of zinc sulfate, the metal that I use as the, here it would be the anode, is zinc metal. Here, if I have copper, I use copper metal. If I have copper sulfate, I use copper metal. And I have, in those boxes in the back, I have to, on the teacher planning day, on my list of things to do is unpacking. I have gotten a bunch of different electrodes so that we can build different cells in a couple of weeks when we do that lab. Next thing. So the electrode is our way, it's gathering the electrons. It allows for the electrons to be transferred through the external circuit. That's at the top. So it gathers the electrons and allows them to flow from anode to cathode. And it's made up of some metal. Salt bridge. These are solutions in the half cell are connected by this medium called a salt bridge. It can be a gel. You can do a salt bridge where you have a gel, and in that gel you have an ionic compound. We're going to do something much simpler than that. We're literally going to take a paper towel and soak it in salt. And that'll be our salt bridge. And then we'll connect the paper towel between the two beakers. So it's just some medium to allow for ion flow. Yes.
Could water be a medium?
It's too weak of an electrolyte. So you have to soak it in a strong electrolyte.
Are we gonna calculate how much, how much ions do we need for?
Not for the salt bridge, no.
No.
Mm-mm.
That'll be cool.
But it allows for, I mean, you could on your own, for ion flow in and out of the salt bridge. Basically, like I said before, you need the salt bridge or you can't complete your electrical circuit. And technically, when you're building a cell, you're building a circuit, chemical circuit, technically. And then voltmeter. I purchased some extras because I know we are running low on working voltmeters. I still don't know if we'll have enough for everybody. I have ammeters and voltmeters. But voltmeter basically measures the reaction in volts. So you put your little alligator clips. I don't know if you remember those from previous, but you had like these little black clips and red clips that you would put on the voltmeter, and it would have a little lever that went up, and that would tell you that you were conducting electricity. So we'll have that as well. So it measures the amount of voltage produced from a spontaneous redox reaction. One of the things about a battery is that you use them, right? So you use them up, meaning eventually they lose their efficacy with time. And so as the reaction proceeds, the cell voltage is going to decrease. And when the cell voltage reaches 0, this means your reaction is at equilibrium, but it also means you can't really pull any more volts out of it. It's not really going to be working well for you anymore. So, next thing. What is standard electrode potential? So this was one of the definitions, right? These were the definitions that Cambridge said they wanted you to know word for word. Define. And I knew that the what is a half cell is coming, so I wrote that right underneath. So standard electric potential, which is called the E value, and you might see E with that little sign afterwards. That little sign afterwards right here means standard conditions. Standard. This is the voltage, so it's going to be measured in volts. This is the voltage produced, so you'll see volts. When a standard half cell, which has a specific concentration of 1 molarity, that's we define the standard of 1 molarity, is connected to a standard hydrogen electrode under standard conditions. What is standard conditions? What do you think standard conditions are?
No, 25.
I heard
The one that was
298 Kelvin, which is the same thing as 25 degrees Celsius, and 1 atmosphere of pressure, right? 1 atm. That's standard conditions. So at standard conditions, what will the voltage be produced when I have a 1 molarity solution? That means when we make our cells, if we want the standard, we're going to have to make what molarity concentrations of our solutions? We're going to have to make 1 molarity concentrations. And if we change the concentration, that's our final lesson for this unit, that actually changes the voltage. And we'll figure out how does that affect. It's actually in specific equation you'll have to memorize called the Nernst equation. So more math. More math.
Should I give us?
They do not. They give you this. You get Faraday.
Yeah.
All right. So standard cell potential is the difference in two electric potentials between your anode and your cathode. And so this is what we're going to be calculating on Wednesday. Next class. Because you won't see this class till Wednesday because you've got a long 3-day weekend.
Yay.
No school on Monday for you. All right. And then finally, what is a half cell? This is 1/2 of your voltaic cell or your electrochemical cell. And it's either your anode or your cathode. So the half cell is where you have half of what's going on. This is a half cell. This is the sheet, which I did tell you that is something they're going to ask you to memorize, the structure of the sheet. She stands for standard hydrogen electrode. And yes, you know in chemistry, sometimes we like to abbreviate. Anytime you're talking about the standard hydrogen electrode, you are allowed to just write sheet. Cambridge allows you to do that. Instead of writing the word standard hydrogen electrode, you can just write the sheet. And they assume that you know what you're talking about.
Hey, that's a half cell piece.
This is a half cell. So this half cell is the sheet. What is in this half cell? 1 molarity H plus. H plus. Where did we get that from? No. Some kind of strong acid. That's 1 molarity. You're not going to have 1 molarity H plus in water. You're going to have 10 to the negative 7 molarity H plus, won't you? Because of pH. You need a strong acid. Yes.
I was gonna, sorry if this is, but why do we separate the
It's coming. It's so that you can harness the electricity out through the wire. Otherwise, it would just be in the solution.
Does that mean that the proportion is constant? Or not constant, but can we, like if we have the voltage of 1 cell, can we get the one of the other?
Yes.
Like it's a closed system.
Yes. Well, not a
closed,
closed system, but a closed circuit. Yes. So you get strong acid. The electrode here is made of platinum. And no, I don't have a platinum electrode. We're not building a sheet. But the electrode's made out of platinum. Then they use this thing called a glass bell. That's this. And so you have to write this actually in your diagram. And so this right here is where hydrogen gas would be coming out or going in and being collected. And so this is where, notice you see little bubbles here? Hydrogen gas is being produced. So the goal is to get the hydrogen gas to go in through here so that you collect H2 or you pull out H2, depending on if it's at the anode or the cathode. And so this is actually, and we'll get to it, when we talk about fuel cells, for hydrogen fuel cells, you use the sheet for that. All right, and then look, the wire is also made out of platinum for the sheet. Again, we're not actually building the sheet in the class. We'll be building 2 other half cells. We'll be building something more like this.
Is it because of the price?
Price. Money for platinum. I think we looked up the price of platinum. It's like super expensive. Your lab fees will not go that far. I promise you, the $10 you pay will not go that far. All right, so we actually are unable to measure the potential of a single half cell. But if we, and the word is arbitrarily, set the potential value of a particular electrode at 0, then we can say everything else relative to that electrode is either oxidized or reduced by a certain amount. So the idea is that we set the Xi as our baseline to 0. That's what we call 0. And then if you measure the electrode of anything, the potential of anything versus the Xi, you're going to find out whether it's relatively oxidized or relatively reduced. And you'll find out what the voltage value is in comparison. So the standard potential for the Xi, either serving as the anode or the cathode, is always going to be equal to 0. And that's why I said that's the only number that you would need to know, that the Xi is always 0 volts. And everything else is compared to that, above or below 0. I'll tell you why above and below 0 shortly. So the standard hydrogen electrode is our reference electrode, another way we can call it. And all other electric potentials, as they have been measured, are based off of this standard. Yes.
Does that mean that if we want to measure the voltage of a particular cell,
You need to do it versus the Xi.
so we
And
have
that'll
to
tell you the
select
voltage of that half cell. You will be provided with values, or what you'll be provided with is the difference between the two.
it? But it's okay.
You'll see, everything's against the Xi. So then, these are our standard conditions. I've already mentioned this. For an aqueous solution, you need 1 molarity. Pressure needs to be 1 atmosphere or 10 to the 5th pascals. Temperature 25 degrees Celsius. And then the value of your electric potential is relative to the Xi, where this is the Xi. So here we go. I believe I told you you would not need to memorize E values. So breathe in and breathe out. You will not need to memorize E values. But what you will need to know is the following. If an E value is positive, all of these numbers are positive, then in comparison to the Xi, that element is going to be, and it says it here, reduced. So if I see a positive value, that means that that is going to be reduced versus the Xi. And if I see on the opposite side a negative value, that means that that is going to be oxidized in comparison to the Xi. So notice here, these are all reduction half reactions, and these are E values that are given to you for these reduction half reactions. If I see a negative here, what that means is that the Xi would be reduced and these would be oxidized in comparison to the Xi. And I want you to kind of link that. So these would be oxidized and these would be reduced naturally. Does it make sense that fluorine would be reduced faster than everything else, or most out of everything?
Yeah.
Why?
Because of the electronegative.
Because the most electronegative element, it wants those electrons more than anything else. Of course, it wants to be reduced more than anything else and would have the greatest E value, which means provides the greatest amount of voltage, provides the greatest amount of chemical energy, right? So if you're trying to supply voltage to something and you want a lot of voltage, there are certain elements you would choose in comparison to others. I want you to think about what type of batteries we use a lot. Lithium. Look at how much voltage it produces if put on the right side. 3.04. Meaning that lithium ion, well, it doesn't want to gain an electron, but it really wants to lose it. Do you agree? Lithium really wants to lose its electron. Because it really wants to lose its electron, it's going to provide that electron as a source of electricity. And therefore, it's going to harness a lot of power, which is why we use lithium ion batteries a lot. So same idea. So lead, we do use lead for batteries, but it doesn't provide near as much energy. And you may notice that the lead batteries are really big that are in your car. So a positive value indicates easier to reduce, and a negative value means easier to oxidize. And so those are all compared to the shape. And so if I have a reduction value and something is going to be oxidized, guess what you're going to have to do with the equation if you have to balance it? You're going to have to flip it whenever it's an oxidation. And so we'll look at the math next time. The math's not difficult, but we'll look at the math next time. But let's take a look at just, this is check of 10 from the textbook, and see if we can answer some questions about the values that were given to you on the last slide. First one says, which metal on the list would be the best reducing agent? Which means, which metal on the list is oxidized? The easiest. What do we think? Lithium, right? Because the lowest on that list. So lithium. Which metal is most difficult to reduce? Meaning, which metal is most difficult to give electrons to? That's not a metal. Which metal is the most difficult to give electrons to? Shouldn't it also be lithium? Because it wants to get rid of its electrons? Be careful with the questions. Lithium. All right. Which metal on the list is technically the most reactive?
Lithium.
Lithium.
Seriously? Actually?
Yes, lithium. Okay. Which metal in the list is the easiest? That's not a metal. Which metal?
See,
Lithium again?
No.
Four?
final four. Wait, yeah, you're right. Oh, yeah.
I guess.
Copper.
Like,
Is it?
iron.
If you're going with a pure, we didn't say whether it's a pure metal or a metal within an electrolyte. If we said that it was just a metal within an electrolyte, it's actually the permanganate, right? It's MnO4 minus is the easiest to reduce.
But isn't that another compound on a metal?
Right. So if we went with pure metal, which was the answer that I had, the pure metal is silver here. Is the easiest to reduce, right? Because it said metal ion, didn't say polyatomic ion, right?
That's lithium.
Silver. I'm gonna write Ag, but silver is the easiest to reduce. All right. That was a textbook question. That came from the Cambridge textbook. Okay, more definitions. Some of them are repeats. Half cell, we already said, is either the anode or the cathode. The voltaic cell is technically when I put the two half cells together. So this whole thing is the voltaic cell, both half cells put together. And so the half cells, you got to know they're connected using wires. We use a voltmeter to measure the amount of voltage. So here it's missing, but you would need to know to write that. So when we write a diagram here, you would actually be connecting your electrodes to a little device called a voltmeter, and it would measure the voltage.
Can you use it like the power light bulb with lithium in that way, you know?
Actually, 1 year, like 3 years ago, we did when we built the voltaic cells. And I mean, I could see, we're about a week and a half, we could try. But last time I did that with the students, we blew all the light bulbs.
Oh.
So the answer is yes. A lot of laughing happened. Can we blow up light bulbs is what you're asking?
No, that's not what we're asking. We're asking if we can do the experiment if the light bulbs happen to blow.
We'll see. I have to see because the light bulbs we had from the company that we got them from were too tiny. So like the amount of voltage was too much and it overpowered them. And then Mr. Cerciani was doing something at the same time with, he used to teach A-level math and they had to like build their own thing. And they kept asking me for light bulbs and I was just like, we don't have any more.
Does this block the screen?
They do.
Anyway, so it's possible.
You
It's
have
possible. I gotta look up or why don't you?
Like a house light bulb.
We can test it. It's something testable over the next couple of weeks. That's something I want to test before we actually do it in class. So telling you that as a reminder after Monday when I take everything out, because I'm taking everything out for this experiment on the teacher planning day. So I'll have everything more set up after that. So yes, it's definitely a thought in mind. Good thoughts. Maybe bad thoughts. Who knows? We'll find out. All right, so yes, it could power a light bulb if you set it up correctly and if you have the right amount of power, right? And so we'll test that. One important difference here that always is actually a little bit confusing to me, but I want to try to explain it as best as I can. The electrons actually still flow from anode to cathode. That always happens because oxidation happens at the anode and reduction happens at the cathode. But the sign of the electrode, meaning what's the negative terminal and what's the positive terminal, is flipped. And usually how I like to explain this is because one process is with a battery and you're forcing electrons to go one way, whereas this is spontaneous, so the electrons are going like it's different. But the way I'm going to try to explain it is here, back in what I wrote over here. Here, the anode is the negative electrode in a voltaic cell. Yes.
Could you use a voltaic cell to charge an electrolytic cell?
Be a kind of complicated setup, like to be the battery.
Oh yeah.
I'd say that's possible, but most people would not choose to do it that way because that's more work than just going out and purchasing a battery to hook up. Just throwing it out there. And this is definitely also more expensive than just purchasing a battery. So yes, it's feasible. Is it something realistically most people do? No. Okay, so I'm talking about right now what the signs are. Because what's happening here is the anode is gathering the electrons from, in this case, zinc. This is actually the negative electrode because this is where electrons are going into. And so the anode is the negative electrode here. The cathode is the positive electrode. Why? If the electrons are flowing from here, they're going into here and they're going here, what's happening at the cathode? The electrons are being released. What does it mean if electrodes are being released from here? If I lose an electron, I become positive, right? So this is going to be the positive electrode because electrons are being released from the cathode to provide the reduction. And that's the best explanation I can give you on why the signs are flipped between the electrolytic cell and the voltaic cell. The signs of, and yeah, you do, and you could just memorize they're the opposite, but there is a reason why the signs are opposite of them. And Cambridge does want you to know the signs. They call it to deduce the polarity, what's negative, what's positive.
So in a voltaic cell, it's like flipped by the other one.
Flipped in terms of the signs of the terminals, like the cation being positive or negative. In the electrolytic cell, the cation is the negative cell. In the voltaic cell, the cation is the positive cell. I love redox. Like I love school. Let's go ahead and continue. So we're finally getting to do something. Write the half equations for the reactions taking place in the half cells below. Now, I thought this year we're going to actually do this really quickly because we've already done that really big lesson a couple of classes ago on how to put half reactions together. So they're telling you to write each of these as a reduction. Can you write this as a reduction? What would you start with, the chromium plus 3 or the chromium plus 2?
Chromium
Plus 3.
Plus 3. Goes to chromium plus 2. And what am I missing?
Plus E minus.
Plus E minus. That's it. Next one. What would I start with? The BR2 or the BR minus?
CR2.
BR2. And that's why I said I think we're gonna get through this real quickly. And how many electrons? 2. Good so far? I'll pause. Okay, so the last and major thing we have to do for the day is you're going to be asked to build this from scratch. Meaning, Cambridge wants you to draw the diagram of any voltaic cell. What do I mean by any voltaic cell? Well, you've got three possible situations. One half cell is you have a metal and you've got the metal ion of that metal. So for example, this would be copper 2+, where the electrode is made out of copper. That's situation number one. How would we build a cell with that? Situation number two, what if you were provided a nonmetal and the nonmetal ion? What would happen there? The electrode cannot be made of the nonmetal. You gonna make an electrode out of fluorine? Not gonna happen. So what changes in your voltaic cell? What does your electrode have to be made of? We'll talk about that. And then what if you have two ions? For example, so here this would be like fluorine minus. What are we using there? And what if we have, for example, two ions with different charges? For example, we've got that MnO4 minus to Mn2 plus situation. Can either of those be used as the electrode? No, they're ions. They're aqueous. You cannot make an electrode out of that. So what would the electrode be made of?
Carbon.
Because carbon is slightly reactive in water, they don't use carbon. We have to spend more money. Like I said, we have no money, but we have to spend more money. So the platinum would be the electrode that you would use if you can't use the metal that it's made of. Yes,
It's highly interactive.
it's the most unreactive, but it's got that great electrical conductivity. It's got great electrical conductivity. It's got the metallic bonding, which allows for the free flow of electrons. It actually, if you look it up, it is one of the most electrically conductive, but it also is super unreactive. So that's why people use platinum. You could use gold. You could. But usually it's platinum is the most common use. All right, so
Well, it's also way more expensive than platinum.
you'd have to look that up. It probably is, yeah. So these are our situations that we have to know, and these are what our electrodes are made of. So what you just have to remember is that if you've got a nonmetal or you've got a polyatomic ion, you're not going to be able to make the electrode out of that. So the electrode's going to have to be platinum in these cases. And so let's take a look at the question here. Cross out this question. I actually this year went and updated all the images from the textbook because I had in the past taken pictures of my old textbook and like put them up. But now that we have a digital version of the textbook, I was able to, copy paste the images so it looks a lot nicer. But a question here changed. There was a question that says, what is the identity of the salt bridge? Obviously from here you can't tell because they just said the word salt bridge. They can't tell you what it's made of. In the prior textbook, they actually had like an ionic compound there, and then you could identify what it was. So let's take a look at this. Looking at copper versus the shape. What do you think? It's oxidized. And so let's take a look back here. Copper is not oxidized versus the shape. Copper is reduced. So how could we figure that out? Like looking at this. What does this positive mean? What does this negative mean? Remember, the positive cell is the cathode. And the negative cell is the anode. So they're telling you this is the cathode and this is the anode. The way that I read it is when I read it like this, I read it as positive 0.34. So I'm like, okay, positive means reduction. That's how I read it. I look at the number and I say, okay, greater than 0, that's reduction. Copper's being reduced. But it's because the signs of the cell will tell you what's going on. Compared to the sheet, copper is positive. Copper is positive, that means it's being reduced.
Why does it matter to be at one hemisphere for the H2 gas?
That's an interesting question. Because the pressure, like how does the pressure affect how much you have that's going in there, right? Because pressure is the amount of particles hitting the wall of the container. It affects how much is going in here. So that could affect your end result for sure. I'm sure Le Chatelier's principle comes into play, which when we talk 2 or 3 lessons, I think it's 2 lessons from now, about the Nernst equation, we can address that more. Francesca, yes, you can scan, show, and go, yes.
Does the mineral from the mineral series have anything to do with this? Because I'm thinking copper is below hydrogen, so hydrogen.
It does, sort of, yeah. Yeah, because also silver's below hydrogen, and silver's also reduced compared to hydrogen.
Yeah, but farther than copper, but is higher than the molecular activity series.
Yeah, I think that's what I think that's all the same. Like, I think you're all saying the same thing. Yes, it is related. Okay. Here you go. All right, we're going to go ahead and continue.
So, what is oxidized? It's not copper. It's hydrogen. What's reduced? Copper. What's the voltage? Positive 0.34. You literally just read it. Next class, we do the math. But if it's 0.34 versus 0, it's 0.34.
Yes.
Yes.
Sorry, I know you don't know this, so I just want to confirm. So in a voltaic cell, the cathode is positive one and the anode is
Yes.
negative, and in the other one it's your.
Yes.
Why?
I tried to explain.
Science.
I tried to explain over here because one is supplying energy and the other one is taking energy. To me, that's what makes the difference. But if you go back here, I brought up how it happens because the anode's gathering electrons, it's taking the electrons, so it's negative because the electrons are going there.
Okay.
Whereas the opposite situation is happening in the electrolytic side. So that's, you have to look at that longer. That's something you have to look at for a while. I've looked at it for years. Because redox is one of those things that gets confusing. It's like switch and then switch again and then switch again.
Yeah, like reduction is reduction of charge. Not
Right. And that reduction of electrons is redox. All right. So these are checkouts from the textbook with my new updated images from the new textbook. Because like I said, I used to take pictures and have the pictures like printed there and it looked really fuzzy. I think I still had last year, maybe one time that I had a picture printed from the textbook, but then I got the brilliant idea. I was like, wait a second, I copied all the pages of the textbook for you all. Let me just copy those images in here. Write the hot equations for the reaction taking place. So looking at this, can we tell if iron has been oxidized or reduced? What's, if you need help, go to the table to help you. Iron has a negative value. That means it's oxidized in comparison to the sheet. So iron is oxidized here.
which iron likes me.
So this right here does not tell you if it's being oxidized or reduced. They just write both variants of iron there, so that's not what's giving it away. Here, yes, iron does like to be oxidized. It does do that. As you know from, I think yesterday?
Yep.
With the big flood. All right, so this right here is where the oxidation is taking place, and the sheet is where the reduction is taking place. And another way to keep that straight, like I said, the way that I read this as negative 0.44. Negative number means oxidized. Yes? So, what's the oxidation half reaction? Fe to Fe2 plus, and the electrons are right there. What's the reduction half reaction? Because you have to have both. Can't have one without the other. What's the reduction happening here? What's being reduced? If it's something against the sheet, it's hydrogen that's being reduced. Well, what's the form of hydrogen that's being reduced? What's here that they're not saying?
Water,
Acid.
water. That's water.
It's H plus, it's 1 molarity acid, right? So what's being reduced? H plus is going to
H.
H2.
Oh.
2 H pluses. Which side do the electrons go on?
Reactive.
Reactant side. Now do you see why I taught that lesson at the beginning to review how to do half reactions? Because it makes it easier when we get to what we actually have to do with it. So now the electrons cancel, bring the rest together. Fe plus 2H plus goes to Fe2 plus H2.
What could the salt break in this equation be?
I mean, I usually just make it out of salt. Everything that I've been able to run, I've been able to run with NaCl. So any salt that's not reacting, that's not part of the identities that's there, just that's there to carry the charge, if that makes sense.
Oh.
Ready to continue? Try another one? All right, looking at this, what's being oxidized? Yep, negative 0.91 means oxidized. So what we've got here is chromium going to what? They tell you. Chromium's going to chromium plus 2 and 2 electrons. So what's being reduced? Which we already said it's the sheet, right? So again, it's H plus going to H2. Balance 2. Electrons go on the left side. Are we good with that? Bring it together. Electrons cancel. Yay. Yes.
Instead of looking at the Voltaic,
The number?
yeah, can we say, I mean, one side is the, I know, the other one's the cathode, so electrons.
What do you mean by one side? Because they didn't tell you the direction of electron flow here.
That's the thing, can we determine the direction of electrons flow with the charges?
With the minimum, you have to have these charges here. Which side is the negative pole and which side is the positive pole? At minimum, you need that
Could
information.
they tell us which way that would choose one?
They could.
The charge?
Or more often, they ask you to draw the direction of electron flow. More often.
It always goes from the
Anode to cathode. What's being oxidized to what's being reduced. Because electrons are going to whatever, to reduce whatever is going to be reduced. All right, try another one. Silver! Is silver being oxidized or reduced? Reduced. So how does that happen? Oxidation half reaction. Ag plus goes to Ag. How many electrons?
I love the fact that the color of the solution is like the color that it actually be.
Oh, in the text?
Yeah.
Yeah,
And the iron on the screen.
yeah.
Yeah.
They updated their graphics. Good update. Nice update. Because beforehand it was not like that. Yeah. You're right. This is the reduction. I'm gonna just write reduction there. I said reduction.
Yeah.
So what's my oxidation? So how would I write that? I just wrote the first thing I saw, the silver side. So H2 goes to what? H plus. Okay, be careful. What's a way we can balance this?
Multiplying the reduction by 2.
I mean, I would just instead, I know that this is only one electron being transferred, right? So could I change this to being one electron transfer to make my life easier? I would do 1 plus here and then just put plus E minus, but you could also do double everything and it would be the same.
Why
Up to you.
more when less writing makes sense?
I think that's your senior quote.
Probably
Pretty sure that's your senior quote. Words to live by. So I get Ag plus 1 half H2 goes to Ag plus H plus.
Always times getting.
Hi.
Alright.
Yes.
Why does it say silver to plus?
What?
Silver to plus.
Where does it say silver 2 plus? Oh, what are they doing? Because they wrote silver plus there. I didn't catch that. Submit that to Cambridge International for a revision for their next edition of the textbook. It should not be silver 2 plus. I literally copy pasted that from the textbook.
That's need to get A marks B on the kind of test.
Doubt it.
Can I send them my Canadian number and be like, hey, so I noticed
Can-
a mistake in.
Can you boost my grade?
Not even. You know, since I found a mistake.
So wait,
Can you change my level up? Yes.
what if we like, okay, so what if like we find a mistake in their like textbook like 10 years after, you know?
I don't know. They probably people have already told them because that's a 2022 textbook.
Can I feel the test limit on that?
Yeah, if we write AGP
Realistically?
plus,
You imagine?
No, I don't think so.
I saw it in the textbook.
Or it's like the question about something completely different. You're like, see, I got here
At that
because
one
in the
time-
book there
at
was
that
one
time there was
Yeah.
a difference. All right. Half cells containing non-metals. Here we go. Remember what I said. You're going to use a
I know.
platinum electrode. And so it's going to look like this. Platinum. But it's not bubbling out, so you don't need the little collection belt for that. So this is sulfur 2 minus. Sulfur, and yes, they did it right. Sulfur solid at the bottom. That's what sulfur looks like as a solid. And then there's sulfur 2 minus in the solution. You're using a platinum electrode. Notice the platinum is going all the way into the solid. So it's touching both parts, the solid and the aqueous solution. Issa, you have a question?
Yes, right. I wanted to ask him the question before. So hydrogen is being oxidized.
Yep.
Hydrogen gas.
Yep.
Where does hydrogen gas come from?
Supply. That's why this is going, there would be a supply of hydrogen gas.
So in this part, there's no acid. Like in this,
No, you have both.
we have both.
You always
Yeah,
have acid.
you always have both. Like it's part of the building of the cell. And then it's just where the electrons, which way are they going through?
And depending on what they made out.
Right. So here you're making silver solid and H plus at the end.
Okay.
Okay. So look at this one. What, and I hate when they do lefts and rights because I don't think lefts and rights is the right way to go with it. They're using, but they tell you to write a half equation for the half cell on the left-hand side, meaning this one. Write a half equation for this.
Yeah, what am I gonna do?
But you could write, like if you're making your own, you can make it on the left or the right side. Like you could put the anode and cathode on either side if you want. That's why I don't like that writing, but they present this to you. So on the left side, what do I have? That's the sulfur. So is that being oxidized or reduced here?
Offset.
The positive number,
It's reduced.
reduced.
Dude, why you say oxide, bro?
Look at the number in front of the voltmeter. That's telling you if it's positive, it's reduced. If it's negative, it's being oxidized. So sulfur is being reduced. So what are we going to do with that? What does that mean is happening? What's the half equation? Sulfur goes to sulfur minus 2 and we're at 2 electrons. Which side? This side, right? So we're putting electrons into sulfur, changing it from sulfur solid to sulfur in the solution here. So aqueous sulfur. And what is the E value? Literally 0.51, right? These are
Do I have to show a charge?
what do you mean?
What do you value do I have to show a charge?
The positive value, I'll double check that on you for the Cambridge questions. I think they can assume that it's positive, but I'll double check. I don't think there's a mark. Like with enthalpy, I know there's a mark for positive and negative. I think they're a little bit kinder here, but I'll double check on that. Yes, these are. Sulfur what? You could.
Yeah, but they let you assume that.
They let you assume that it's S, or you could do S8. It will make your life more complicated to do that though.
You could just do 1/2 essay.
1/8 S8. They'll do the same thing. All right, now it is time. Draw a diagram. First of all, does that mean pen or pencil? Pencil. Draw a diagram to show how you would measure the standard electric potential of iodine. So, what would we need to do? How do we build this from scratch? You'd need a bucket. Usually we go with a beaker. What we're doing with beakers, but okay. You need one for your bucket.
A bucket.
For your anode and your cathode.
In front of
Guys, we're free.
Okay, really important here, you need to include a water level. If you don't include a water level, they're gonna think that you put it in air.
That.
You have to include a water level. Notice that's the water
How
level.
will you do it for a gas?
With, it's still in an aqueous solution, but you have to include like the little bell with the thing. Okay, so are we good so far? Now, I'm gonna choose a side to be iodine and choose a side to be the sheet.
Not that side.
So I'm gonna do the left for iodine
So we have to assume that.
and the right is the sheet. You have to know iodine's solid, yes. So, what else do we need to include?
Ground up iodine at the bottom.
So bitch.
Or just call it I2 solid. Like, you don't have to show that. They accept you writing I2S and I minus. Right? Okay, what else?
The bubbling for the H plus.
I would say we have to dunk something in here. We have to dunk an electrode. And we have to say that electrode is platinum.
Hey, Miss, what is this? What's the naked part? I minus?
Yeah,
Wait, what?
that's the other part of the cell. Like this is solid and this is AQ. All ions are aqueous in water.
Wait, does that make that's is that a question that can come back to the food area to 1/2 I2, which makes 2 ionics,
Yeah, that is an error. This should probably be I2
and then 2 electrons.
and 2 electrons. There's one of the sides had a corrected error. That's me typing it out though, so I typed the error. All right, so what next do we need to include?
Salt bridge.
Sure. For Cambridge, all you gotta write here is salt bridge. That's accepted. But the salt bridge has to go past the water level. Like if you write a salt bridge and then you stop it there, again, it's in air now, so it's not gonna complete the circuit. So you've got to have the salt bridge go through into the water
That
level.
will be air bubbling for the sheet.
Hold on. So next thing, we need up here to have a voltmeter. So they accept if you write like a little letter V at the top. That's you measuring your voltage.
So you put +5, plus 0.54 there. Like in the voltmeter area.
You can.
Yeah.
Okay. On this side, and I'm not the best artist, as you all are well aware, but we need to have another platinum electrode for the
Sheet.
sheet. It does not have to be done to the bottom. But this is
The first
where
one.
you have your little bell, right?
Yeah. Wait, there's no way you have to remove some water? Because doesn't the platinum electrode have to touch a gas?
No.
Oh.
Look. No. Oh, yeah.
Mm.
I can't drop. Okay. I think that they wouldn't be, but maybe they would be picky. So here.
Yeah.
Platinum electrode.
Bring it up on another name.
Okay. And then what goes here is the H2, right? And then what's in here? H plus. AQ. AQ.
Wait, Miss, wait, is
Could we
there water
have
in the?
What else are we supposed to write? We're actually technically not done.
Bubbles or something?
Conditions. What are the conditions?
The under reflux? I don't know.
No.
No.
298 Kelvin.
Oh.
1 atmosphere pressure. And you can either write, if you can fit it in here, or you can write it on the side. The concentration matters. What's the molarity?
1.
1 mole, DM minus 3 solutions.
1.0.
Alright, so question.
Yeah.
So the I minus, that just has to be in solution. Does it matter what the cation is?
No.
So you could have HI on both sides?
I mean, you are going to have a little bit of HI because it's water. But typically, like if this is getting made out here, then if this is just water in there, whatever salt is coming in from the salt bridge, it probably was present in there. All right, this is the diagram. Yes.
So, because in the AI one, is it just a solution with solid iron?
Yeah.
Yeah.
It's like that?
Yeah.
So there's water.
Yeah.
Can that detect anyone?
I don't think so. This is what you got to remember. So, how many marks is this setup worth?
2.
Typically 3.
Oh.
3 marks.
3 marks for like 3 minutes.
2 marks for this. 1 mark for the conditions.
So I'm getting
So-
2 more.
Oh, wow. This is another example. Notice here they've written the 1 molarity for everything that's in the solution. And look, they're doing for manganese purple. How nice. Very pretty.
You never had a temperature.
They did right there.
Oh,
Look at
I'm
this.
just blind.
They're right there.
I'm just blind. I don't know.
All right, we're gonna do 1 more of these from a Cambridge question that we're gonna create from scratch. Very exciting.
In real life.
This can show up on paper 4, and it's kind of often does. This is pretty common. Shows up on paper 4, or it could be one of your 2 questions on paper 5. There's a non-zero chance it ends up being your experiment for paper 5. Yes? And I would like that, actually. I think that these aren't that hard to build once you have the idea of what's going on. Okay, Cambridge question time. And I believe it is 3 marks. I forgot to print it at the side, but I looked at it last night. I believe it is 3 marks. An electrochemical cell set up to measure the E cell of iron versus chlorine. What is a labeled diagram of the cell? Include all necessary substances. It is not necessary to state conditions. So that means you do not have to state conditions for this specific question. So what would you still need to include? Go ahead and start drawing it out. Pick a side for iron and pick a side for chlorine. Does it matter? Like if you're building a cell yourself, does it really matter which figure you put on which side?
Would you have to use a different sulfurage than NaCl because Cl is one of the.
You should use sodium sulfate here. So
Need to jar your buckets.
I guess our water level may be like this. Try your bucket. That's wild. Please don't write bucket on a paper, do that. On a paper 5. We do this reaction in a bucket. It's like backyard chemistry. Backyard chemistry. Okay, so then we do here, we have a salt bridge. What side do we want to do for each one?
Left,
Alright,
right.
Iron on the left and chlorine on the right? Okay, sure. So iron has a +3 charge in one form and a +2 charge in the other. So what should our electrode be made of?
Look, iron.
Actually not.
I know.
Platinum.
Oh, I drew too far down.
Hey, why that?
Because if you have a metal ion on both sides, you're not actually getting the metal. You don't have the pure metal there as part of the process.
Oh,
So you use platinum instead. Something to, because the pure metal might interfere. So platinum. And then in here would be Fe2+ aqueous and Fe3+ aqueous. Good so far?
Yeah, the pure metal would probably make it Fe3+, Fe2+, and Fe.
Right.
Yeah.
So it would interfere. So you're going to use platinum if you have ions in multiple oxidations. So then, what do we do now?
why is there no sign this time?
No what?
No sign. Like you put the sign for the other one.
There's no solid here. Iron 2+ is not a solid.
Oh.
Iron 3+ is not a solid. Standard states is why. Iodine is a solid. You have to know elements and their states. You'll see something else come up here then if you have that question. Hold on. On the other side, what do we got going on? PT. What's in here?
Yeah, sure.
Cl minus.
Yeah, hydrochloric acid.
We have.
That's probably your source of Cl minus. That makes sense to me. And then here you've got your fold, and coming out of here, I can't draw, but we can use pencils. So thankfully, that's a thing. Here we have what coming out? Possibly or going in. So you have basically a basin that they're not showing that you would collect the gas in. So some kind of container you could collect chlorine gas in.
A bucket.
Not a bucket. What are we still missing? They said you did not have to include.
The plus minus.
I would put gas here. I would put AQ here. We don't know which side is the plus side and which side is the minus side because we don't have the E values technically. I mean, if you're kind of understand what's going on, in comparison, which of these do you think is more likely to be reduced, chlorine or iron?
Iron loves to be oxidized.
So we can even go back to the numbers.
Minus
Chlorine is going to want to be reduced, right? So you could reason it, but they will give you the numbers later on in the question. This is just part of the paper question. Okay. So where are the marks? I believe I wrote them down. Where does Cambridge award marks in this question? 1 mark for any 3, and these are the 9 things they wanted you to have. Do you have a salt bridge? Do you have Cl2? And do you have platinum as your electrode?
What about the
For
bucket?
the-
Is it always gonna be platinum?
That'll come in. It's not always gonna be platinum, no. Not if it's the metal you're made, like, that's back to here.
Right.
If it's the metal it's made of, so for example, if it's chromium and chromium 2+, the rod is actually made out of chromium.
Could you use platinum and then have chromium sitting at the bottom?
What do you mean?
Like a platinum electrode and then have chromium sitting at the bottom?
I think you could, but money.
This is chromium expensive.
Platinum's expensive.
Platinum is the expensive thing. Voltmeter, Cl minus, another platinum electrode. And then, did you complete your circuit?
Hmm.
So that means, did you make sure the salt bridge went into your water levels? If you don't have water levels, you don't have a circuit. Do you have a good delivery system? Meaning, that's this. Good delivery system is that. Good delivery system.
That's probably where they would take away the mark if the platinum was
Right.
the air.
Yeah. And then, do you have Fe2+ and Fe3+? Both in the solution. So these are the 9 points, but this is worth how many marks? 3. So you count up how many of these things you got, and that's how you would earn the up to 3 marks. And so for your final question of the day, and guess what? We did a beautiful job. We're in the final slide of the last part of class, and it says, guess what? Your turn. So you get to make your own cell for this diagram. This time you do need to have conditions. So go ahead and draw the cell over the end of class, and I have a little something for you as we go.
Like, do we have to do the problem?
Yes.
And they give us a salt bridge. And they put our buckets in already.
Stop calling it a bucket. Oh.
Her spirit is wild. Sophia, do you have all of the M&Ms? All right.